So today we will start chapter 9. Chapter 9 talks about the regular languages. Um, we saw a lot of details about regular languages with respect in chapter 7, 8, and chapter 6. Actually, we start this from chapter 4. We talk recursive language, a recursive way of defining the language. Then we find the way to write the regular expression to represent, to define the regular language. Then we find the way with respect of FA to define the language. Then we learn how to write NFA to define the regular languages. Then we learn how to write the transition graph to define the languages. And then in chapter 7, I believe, we learn that find how we combine two regular languages when we have the FAs of that, or how we concatenate two regular languages with respect of their FAs, how we find the union of two languages when we have with respect of finite automata FAs, or how we find the clean closure property with respect of FAs. Today, and then you will saw all those tedious, long, lengthy methods where you need to draw two tables and then you draw the machine accordingly. Today we will see something very close to that, but this will not be with respect of FA. This will be with respect of transition graph TG. But it all talk about the regular languages. So a regular language is a language that can be defined by a regular expression. We already know that, and we know that when we talk about a regular language, it means it must be represented. I'm repeating this with respect, it must have at least one regular expression, minimum one FA, minimum one TG, minimum one NFA. It's not possible that it is a regular language and it missed any one of this. So now there is a theorem here that let's say if we have two regular languages, let's say one first regular language is represented by L1, and the second regular language is basically language 2. We don't know what is this language. Then if you find the union of two languages, it will still be the union. It will still be the regular language. If you find the concatenation of two regular language, it will still be a regular language. It will not change. The resulting thing will not change the behavior of this language. And if you find the closure property, clean closure property, or star closure property of your language, it will be infinity. It will be a universal set, but still its scope will be a regular language. Its behavior will not change. It will not be converted into any other language. Like we have so many other languages like non-regular languages, context-free language, context-sensitive language. So there are a number of other languages. So now L1 plus L2, you all know what does it mean. It means we are interested to find the union of two languages, something which is one job which this language 1 is doing, second job which this language 2 is doing. Is it possible that you find the union of that? So you combine both languages and make one machine which can perform the job of these both languages. So it can accept all words which is present in the language 1. It can accept all words which can be present in language 2. So it's a union of these two languages. Okay, so this is what does it mean by L1 plus L2. L1 dot L2 means that you have two languages. One is L1 and one is L2, and you want to combine both languages in a way that order matters here. It should create a new language which will accept all words which start from language 1 and which ends with language 2. So order matters here. In case of plus, order does not matter because that is a union. In case of dot, in case of L1, L2, implicitly it has dot there. So here order matters. Your all words start from language 1 and all words end with language 2. When we talk about L1 star, so it means that we have a language, and this language is doing something, it is representing something, and we are interested to find the clean closure property of that, and this will be represented by another language, and that will also be a regular language, and its basic building block will be all the words of this language. So this is the basic building block of this one. So it means that in case of L1 star, summation is equal to L1. So L1 is the summation of that. It is the basic building block of L1 star is L1. All the possible words which is present in L1, you can use them individually, or you can permutation of all them with themselves or any other word belong to that language as many time as you want. This will generate L1 star. We saw this in very much detail with respect of FAs. Today we will see with respect of TG. And this is again this slide, you already saw this slide uh, in the previous chapter, that what is the recursive definition of all this discussion what we just did. It says that if you have L1 and L2 are regular languages, then there exists regular expression R1 and R2 that define them. So we already know that regular languages can be defined by regular expression, and those regular languages associated with so if you have this language, so it is associated with this kind of regular expression. If you're talking about this language, it is associated with this regular expression. A combination of these two, concatenation of these two regular expression, which will represent this. And if you have this language, it is represented by this kind of regular expressions. So if and this, and we know that this all belongs to the regular language. This is what does it says that we saw this in very much detail, how we define that, what is the recursive definition of the regular languages. We saw this in previous slides, previous chapters. It is the same slide we have here, but today we talk about with reference of TG. When you talk about TG, it is very easy. It's not that complicated the way you did this with respect of FA. So now if you see here, L1 and L2 are two regular languages. There must be TGs that accept them. So now we are saying that, let's say, if you have a language 1, it can be represented by regular expression, it can be represented by FA, but this chapter talks about TG, so now we say it can be represented by TG1. If you have language 2, this is completely different language from language 1. It has a separate machine for its representation, and let's say this is TG2. So now, and this is written here. So now we can transform these TGs, transition graphs, into transition graphs with one start state and one final state. So you know that by definition, TG may have one start state, may have more than one start state. But when you have more than one start state, so this is non-deterministic, machine will confuse that from which start state we should start. So now what we will do, we will merge all the start states and we will convert them into one start state. It's very easy process. You have as many start states here. So delete the start sign and create a new state and put the start sign there, and this will be lambda. And this way you can reduce multiple start states into one start state. Exactly, you follow the same method with the final states. You know by definition, TG may have no final state, may have one final state, may have more than one final states. So now if your TG has more than one final state, so you want to reduce that into one final state. So how you do that? So let's say you have multiple final states here. So you delete all the plus sign from them and create a new state and put the plus sign there and connect these final states with this final state, and the label will be lambda. So this way you will reduce your machine which has multiple start states and multiple final states into one start state and into one final state. So something which is non-deterministic machine, by doing this we can convert that into deterministic. But okay, so that's the idea behind that. Now if you see, it will look like this way, in this way. Okay, so now we are saying that, okay, we have this machine here. This is it is abstract information of your TG. This TG is doing something. It has some states in between. Here we are not talking about that because we do not have any concern about that. We are just learning how we combine these both machines. So we just draw the abstract machine of that language in form of TG. So we are saying that we have this one machine which represents one language, which is language 1, L1, and then we have this second machine. This is again second TG, which represents the second language, L2. And because this is TG, so we are 100% sure that both languages are regular languages. So now our job is how we perform L1 plus L2 into for these two languages. It's very easy. So you need to introduce one new state like this and delete the minus sign from here, connect these states with the incoming edges with the label lambda, and that's it. So now this is a union of both machines. So now if you see that if you have a word which belong to this language, you start from here and you go on this side. If you have a word which belong to this language, you start from here and you go on this side. So this way this way you can this is a new machine which has the ability to perform L1 union L2 with respect of TG, and this can accept both words. Order does not matter here, and that's the way that you introduce the lambda labeled edges, and this way you can create the L1 plus L2. It's way easier than perform this operation with respect of FAs. Now look at this one when you are dealing with L1 plus L2. So L1 plus L2. So we are talking about that we have one machine here. This represents our L1, and we have another machine here. This represents L2, second language. Our job is to perform concatenation operation L1 dot L2. Okay, L1 dot L2 actually means L1 L2. But here in this case, in this case, L1 plus L2 is equal to L2 plus L1. It does not matter. Order does not matter here. But in this case, L1 dot L2 is not equal to L2 dot L1, because here if L1 dot L2 means your word start from here and finish with L2. L2 dot L1 means reverse of this machine. This should be at the first place and the L2 L1 will be at the final place. So now if in this case what you need to do, you need to combine the final state of the first machine with the start state of the second machine with the new edge and put the label will be lambda, and delete the final state of this, the final sign of this, because this final sign does not matter now. Our word when we reach here, it should not be accepted because we are saying that L1 dot L2 word should be accepted when you are here at this final state. And this star sign, we will delete that because this does not matter here. Word should not start from here. Word should start from here, from the L1. So we delete the final state of the sign of the final state of the first machine and the start state of the second machine, and combine these with this thing. And now you imagine that if you have, if because TG may have multiple final states. Now, if you have multiple final states here, it will be hard for you to connect all these with this. So in this case, first you reduce your this TG with multiple final states into one final state, and then just imagine if you have multiple start states here, it will be hard for you to manage all these things. So then first you reduce your multiple start states of, if that is the case, of this second TG to one final state, one start state, and then you combine your final of one unique final of this first machine with the start state of the second machine, and this way you can perform L1 dot L2 operation. Okay, that's it. You don't need to create the tables and all that stuff. So this is quite easy in this case. It's not hard. So now in case of clean star, we are talking. So you know that when you are talking about clean star, what does it mean? It means that it can generate all possible words, plus it can generate lambda. So now let's say you have a machine. This is your TG, and this TG is doing something. Uh, TG1. This is a start state. This is a final state. So how you make this TG as a clean star? So combine the start state with the final state, and label will be lambda, and another edge which goes from final to the start state, and the label will be lambda. So this way it means that if you are here, you can come here without any input. This will allow you to accept a word lambda. And if you are here, you can go back here. This will allow you to take a write, multiple writes on the same machine, the cycle, and this will allow you to perform all possible permutation of using these words. And you can generate multiple words considering these as a basic building block, and you can generate more words with that. So this is very easy. So just need to introduce uh, the lambda labeled edges from start to final and from final to start. Remaining machine will be remain as it is, and if you introduce these two edges, so this will generate or convert your L1 into L1 star. So this is written here in more good English, so you can read here. And all this will still remain the resulting machines which you generate by these TGs. It will still remain the regular language. It will not change the behavior of the regular language. In future, you will see that we will perform some operation with the regular languages, and with some other kind of languages that will change the behavior of the regular language and convert that. Sometimes they will keep them into regular language, sometimes they convert them into any another kind of language. We will see in future. So that's why it is very important to mention here that when we perform these operations on the regular languages, it will not change the behavior of these languages. In this case, it will still be a regular language. Its scope will still be a regular language. So I hope that this is not hard. It's easy, and it's quite straightforward. Now that's it. Now we will see some more examples which will show us some of these behaviors which we just studied. We have this TG. First of all, we want to see that. So can I say that this is a valid FA? Can I say that this machine is, oh, sorry, this machine is a valid FA?
I don't think it's a valid FA.
Yeah, no, because it's non-deterministic. Top state has two A directions.
Very nice. Can we say that this is valid NFA? Non-deterministic finite automata?
I would say no because it doesn't deal with garbage collection in the final state.
But you know that this is the property of NFA. I'm not talking about FA. I'm talking about NFA. NFA is the relaxed version of FA, and it allows you to be easy on garbage collection.
Oh, okay.
Okay. So now what are the checks we should run in our mind to see that if it is valid NFA or not? We should NFA always accept letter by letter from on the edges, the way FA behave. So we will see that we will have A, separate B, separate A, B. So all letters here. So it pass our first check. NFA must have one and only one start state. It has that, it passed that check. NFA does not have restriction to have a final state. It may have one no final state. It may have one final state, it may have more than one final state. So it has one final state, so it is solely fine with that. Garbage collection, it does not care. It is non-deterministic. It is non-deterministic. You see, you have one A here, you have another A here, and that's it. So we can say that this is valid NFA. And for sure, if it is FA or if it is NFA, by definition, all these are valid TG, because TG is all these FAs by definition are TG, all NFAs are by definition, they are also TG. So yes, this is valid TG also. Okay. So now we can say that we will see what this TG is doing. So it starts, so how we see that? So we need to see, we need to see, it is written here, but if we want to do this job by ourselves, so how we, what is the thinking process of this to figure out that what this TG is doing? We need to, so if we need to find the shortest path, start from the start state and how it finish at the end state. So it requires one A and second A to reach to the start state. Okay, and then it requires one B and the second B to reach to the final state. Okay, so this is what we just figure out that it is doing this. Okay, and now we this is, and we write that. So it means that we have two options: either we choose this path or we choose this path. And how we say this in terms of the regular expression, or by writing the plus sign. So our word can start from A, end with A, start with B, end with B. And now if our word start from A and it can end with A, and in between we do not care, we have a self loop here, and it can be either A or B and as many times. And how we write this? By A plus B whole star. And now same is true here. From if we start from B and end with B, in these two B's we have A comma B, and it is a self loop. So self loop means as many times at this state you can have A or B or combination of this. So it means that we should have A plus B whole star here in this. And this is a regular expression of this machine. Okay. And now we can say that this machine gives you guarantee whatever the word you will have in this machine. We don't care about the length of the word, but this machine gives you guarantee that all words start from it from the same letter and it ends with the same letter. If it starts from A, it will finish with A. If it starts from B, it will finish with B. So the words that begin and end with the same letter, this is the English description of this language. Okay. So now after writing all these things, we can see that this is another uh, TG, I can say. So now for this one, for this machine, you, for sure this is not a valid FA because it is not taking care of garbage collection. Is this a valid NFA?
No, because it has multiple letters on a single edge. It's a word.
Excellent. So it is not a valid NFA either because it has a word as the label of your edge. This is not the property of an FA. FA always accept letter by letter, not a word. So yes, this is not FA. This is not valid NFA. This is only TG. And then this TG says that it gives you guarantee. We don't care from which what should be the start of the word. We don't care what should be the end of the word. Because of the self loop, we don't care the length of the word, but this gives you guarantee that somewhere in this word, either exactly at the start or exactly at the end, or somewhere in between, you must have A, B, A there. And because you can start with anything, so start here. You can end with anything, so A plus B whole star here. So this is, and how we write this? By because of this loop. You have this loop. And this is the regular expression of this machine. It is written here. So word that contain ABA. So this gives you this guarantee. And the same, if you want to use more resources, let's say for some reason, so then you can draw the machine by this way also. Actually, no, this is not the same. No, yeah, this is the same machine. So it is the same machine. It is not accepting lambda, but we just introduced lambda just to have more states and doing the same job. So now, but the language will be same. It is just like different TG with the previous one, but represent the same language. Okay, so that's good. Now our job is to combine these two machines. This machine is doing completely separate work, yes, and this machine or this machine, they both are doing completely separate work. Is it possible that we can create a new machine which can do the job of these both machines? Yes. So take the first machine, take the second machine, and then delete the start state of this and introduce a new state here, which is start state. Combine this with lambda here, lambda label edges, and that's it. And this is your new machine, which is basically L1 plus L2, or you can write that L2 plus L1. It is the same thing. Uh, and it is basically union of these two machines. This one machine can accept all valid words accepted by this machine or all valid words accepted by this machine. And if you see that how we write the regular expression of this machine, so first we write the regular expression of first machine or write the regular expression of second machine. Simply combine the regular expression of both machines by plus operation. So R1 plus R2. This is what, if you also see this thing here in this definition. Look at this one. L1 plus L2, R1 plus R2. So combine their regular expression. So we just combine that. Okay.
Would
Yes.
this combined machine be an NFA as well? Or oh no, it wouldn't, because the
No, this is not NFA. You already give answer, because you see, uh, if it was only this machine, this first machine, when if we just talk about this, yes, this is NFA. But now this whole thing will be one machine, and this violate the definition of NFA. So this new machine, which is L1 plus L2, this is not NFA. This is just TG.
okay, thank you.
So now we can say that is it possible to perform L1 dot L2? Yes. So you should be very much sure what should be the start state of this machine, what should be the start language, and where what will be the final language. Like, you should know the order, which should be L1, which should be L2. In our case, this is L1, this is L2. We combine the final state of this with the start state of this machine, and label will be lambda. We delete the sign of the final state and the sign of this start state from here, because now these signs does not matter here, because this sign is important and this sign is important. Word should start from here, end with here. And now that's it. We combine these two machines, and this will be L1 dot L2. And how we write the regular expression? This is the regular expression of L1. This is the regular expression of L2. Instead of putting plus sign, we delete that. Implicitly, it has dot sign here. You do not need to write that explicitly. Implicitly, it has a dot sign. And this will be the regular expression of this machine.
So the dot product is concatenation.
Dot product is concatenation, and plus is union.
Okay. And I'm so what was the I kind of didn't realize that. What is the process for um unifying or yeah, creating a TG from two with a dot product? It's so you basically just take the second one and put it in with uh a lambda. No, it's not what it's called.
Yeah, exactly what you're saying is right. So idea is that you want to combine both machines in one machine in a way that you want to create a new. So now, okay, what is the practical implementation of this? Okay, so look at this one. So initially we have, let's say we have this machine, And this is when we start our automotive. So let's say this is a machine which is doing something, creating some parts in the auto industry, and this part is first you create this part, and then someone else in another industry, you are not doing that job, and that will use these parts which you create here as the input of this machine, and then they use that part, and then they create the remaining part of the machine. Yes, this is something. And these work is done by two different factories, let's say. Now you said that, okay, while I'm doing that, I am good enough to do that job also. So then you create this second machine also. But now when you create a second machine in a separate area, so you need to deploy more resources there. So now, is it possible that at the same place where you have installed this machine, you can install this machine also as a continuing machine of this machine, and use the same labor or minor addition of the labor, and then you can have the you can build both machines at the same, both parts at the same place. So now what you're doing, you are creating the part from here and giving that as an output, and that will take as input for the second machine, and it can generate the second part, and final product will be delivered. So exactly this is what we are doing here. So now we have this machine here, we combine the second machine here, the final, we delete that final state and the start state, because now we are not starting from here, we are not ending here, we start from here, and then we end here. So this is now the whole thing is one machine now. That is what is the use of this.
So what if you have multiple end states on the first machine?
Exactly. So that will be create a problem. That's the reason that we reduce that to the one final state and the one start state. So then
Oh, okay, okay.
it's very nice. Your questions are very valid. So that's the reason that to avoid that complexity, so before we do that, let's say might be it has multiple final states here, so we reduce all those final states to one final state. And might be it has multiple start states here, we reduce all those start states to one start state here, and then we combine this with lambda, and the direction will be like in this way. Make sense?
Yep, I forgot about that stuff. I got it.
That's great, no problem. So that's the idea behind that for these machines. And remember that in one chapter we discussed that the circuit board. So you have the logic gate. You can convert that into the Mealy machine and the Moore machine. So that's also related to that. So once this is the soft idea of the machine what you have in your mind. Yes, and then. And then you convert this into the hardware. So then you convert this into the circuit diagram, and then you draw this onto the hardware, convert this soft idea into the hard idea, into hardware, into exactly something which is workable. And that's the idea behind that. So now let's see how if we have the machine which is L1, and we are interested to find the closure property of that. So it's very simple. So you just need to connect the final state with the start state, label will be lambda, start state with the final state, label will be lambda. That's it. Job is done. And this, look at this one. This is the regular expression of this machine, and you put everything in parentheses and you put star outside. So this will be the regular expression now of this machine. This is completely different machine now. This is completely different regular expression. This completely changed the meaning of this one. Yes, but this is the idea behind that. And now if you have this machine, exactly you perform the same job. You put this here, and then you combine this with this thing, label will be lambda, and now this will be a new machine, but this will be clean star now. And how you present that, so whatever the regular expression of that, put the parentheses around that, and then the star outside, this will be the regular expression of this machine. And this is completely different machine from the previous machine. So that's the idea behind that. Then if this is good, see if everybody's writing in chat, no? So let's go to the complement of a language. Complement is very easy. You must know that what is complement. If you have you are aware of the ones complement. So means that if you have something yes, and the complement will be no. One complement will be zero. Zero complement will be one. true complement will be false, false complement will be true, no complement will be yes. So this is whatever the state, the reverse state of that. So that is the complement of this. So this is very easy in to implement the complement in the language. So we are saying that if you have a language L, and if you are interested to find the complement of that, so how we represent that? We will represent the L dash. L dash is the complement of a language. So I do not, somehow I don't know why I did not find how to put dash here at that time. So I put comma here. I should fix it sometime. So it is not comma, it is dash actually. So this is a complement. So now if you have a complement and then you again take the complement of a language, this will bring back the original language. So you have a language, you want a reverse of this language, so you take the complement. You want to get your actual language back, take again complement. This will give you the actual language. Okay. So now if I say complement, if I say a language and I'm interested to find the complement of that, so any one of you, can you please explain me what does it mean with respect of the language? What is the resulting thing you will get when we talk about the complement of a language? Anyone? So we have a language, and I'm asking you find the complement of this language. So when you take the complement of a language, what does it mean? What do you understand by looking at this? So this is the reverse of the previous state. If it is no, it is yes. If it is one, it will be zero, zero convert into one, true into false, false into true. So what is the complement of the language mean in our case?
Is it like the set of all possible words that aren't in the language?
In the language, yes.
Using the
So,
same alphabet.
so it means that if you have a language and it is accepting some words and some words are not valid, are rejected by that language, so the complement will be reverse of the language. So it means that all those words which are accepted by language, now it will be rejected by its complement, and all those words which are rejected by language are now by accepted by its complement. So now, so because this is the reverse of the language, yes. So now if you see this, we have summation is equal to a comma b, and we have a language. Let's say this language is let me click. So this language is basically all words containing AA. So it will have all words which must have AA. So the reverse of this language will be all words does not have AA. So this will be reverse of this language. So L dash, language of all words that do not have a double A. So this will be complement of this language. See, and how we represent that by L dash, and if you take the complement of that, I already explained that you will get back your actual language. Now let's see the example, then might be you will more understand. So if L is a regular language, then L dash is also a regular language. So if you apply the complement on the regular language, it will still remain a regular language. So there exists a FA that accepts a language L. All words accepted by this FA and in a final states. All words that are not accepted and in a non-final state. So how we reverse? So we reverse the states. So let me show you what does it mean. Then you can understand this. Look at this one. So we have this language, and this is a language. So this language will represent only one word or two words, A, B, and if we pick A from here, then A, B, A, or A, B. If I pick B from here, A, B, B. It will only represent these two words. So when we talk about the complement, it means the complement of this language will not accept these two words, but it will accept every other word than these two words. So all those words which are rejected by this machine will be accepted by this machine, and will be accepted by this machine will be rejected by this machine. Okay, so this is basically the reverse of this language, this machine. So how we achieve that? It's very easy to do that. So look at this one. So we have this plus state. How we know that which word is accepted in this machine? When word will finish, any word, it will finish at this state, it will be accepted by this machine. So what we will do, we will reverse, we will delete all the final states of this machine, and where you do not, those states which are not the final states, we can make them the final states. Look at this one. So this is non-final here, we put plus sign here, non-final, we put plus sign here, plus here, non-final, we put plus here, non-final, we put plus here. This is final, we delete that. So this is not final here. Now look at this. It will not accept A, B, 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 but other than these, it will accept everything, whatever word will finish here. And in this case, any word finish, any of this state will be rejected. Only this is the criteria to of the acceptance. Here this is the criteria of rejection, and everything will be accepted other than that. So you do not change any label, you do not need to change any direction of the label edges, or no need to delete any state or add any state. Just reverse the final states. Whatever the final state is there, delete that, and whatever the non-final states, make them the final state. So this is language, this is complement of that. This will be reverse of this language. That's it. It is so easy. And now if we read that, it will make sense. We reverse the final status of each state. All final states become non-final states. All non-final states become final states. The new FA accepts exactly those words that are not in the actual language. Means it reject whatever the words which are rejected by that language will be accepted by this one. And by Green's theorem, L star, and this is also a regular language. L dash is a regular language. The resultant thing is a regular language. It will not change the behavior of the language. So this is your what do you call, complement of a language. And now we can see this. We here it says that L1 and L2 be two regular languages. So any question, guys, here about the complement? We finished that topic. You guys happy with complement? Okay. So now we are saying that if we have language one, and if we have language 2, and these both languages are regular languages, and we are interested to find the intersection of that, how we will find that? So there are multiple ways to find the intersection. The one way is you need to convert this language, you need to follow this formula, De Morgan's law. This way you will find the intersection of both languages. So what you need to do, first take this language L1 and find the complement of that. Then take language 2 and find the complement of that. And the complement will be a new language. This is a new language, this is a new language. Then remember in chapter 7, we learn how to find R1 plus R2 with respect of FA, that tedious process where you need to perform two tables, and here is AB and all the long job here. So you need to perform that operation here, L1 dash plus L2 dash, okay, on these two new machines. Find the plus sign. So once you do that, this will give you this new transition table, and from this transition table you are able to draw a new machine which will be representation of L1 dash plus L2 dash. Once you get that, this new machine, so you need to perform the complement of this machine. Look at this one, complement of this machine, that is equal to L1 intersection L2. So this is the intersection of these two machines. Any confusion here? How we do that? Because we already did this process before. We just need to take a complement and that's it. This is a new thing, but this is the old process what you already done before in chapter 7 in very much detail. Okay, so this is one way of finding the L1 intersection L2. There are another way also. Uh, First of all, is there any confusion here how we find L1 intersection L2? Okay. If there is no confusion, so let me go move to the next slide. So I think that this is the example of this machine. This is our first machine, and this is um, valid FA. If you see that it is letter by letter, exactly one start state from this state A, B, from this state A, B, from this state A, B. So this is valid FA. It is taking care of garbage collection. It is deterministic. And what is the language it represents? It represents any word start from either A or B. And there is a loop here, but end with anything else, no problem. But to reach to the final state, you must have two consecutive A's. So words with double A. So this machine gives you guarantee that to reach to the final state, you must have somewhere in your word double A. So this is basically the regular expression of this machine. So how we write that? We can say that A plus B whole star B, then uh, A plus B whole star. Yes, so it is here also. You can see this thing. Okay, and now we have this another language. It will accept lambda. It can start with B. It can start with A. It can have multiple B's here. It has A. It has to go here A also. So this language gives you guarantee that to reach to the final state, either you will have lambda because start state is the final state, so you can accept lambda, or you may have just one B, or you may have more than one B to reach to the final state. Look at this one, B star. B star will give you lambda, one B, or more than one final B. But let's say you do not follow this path, you go to this path, then this gives you guarantee to reach to the final, whatever the size of the word, we don't care. You can have as many right here on this B, but you must have 2A, minimum 2A's must be there, 1A and second A. In these 2A's, you can have as many B's if you want. And how we can write that? A, B star, and the whole thing will be star. Might be you do not choose this path, so whole thing will be star. So this whole thing, because you just choose this path. So to represent that, we have this regular expression of this language. Okay, so words with an even number of A's. So this is the English description of this language. So now we have these two languages, and these all are valid FAs, and we are interested to find the L1 intersection L2. Okay, how we do that? So we just learned this De Morgan's law. We need to apply this De Morgan's law here. What does it say? It says that you are interested to find this. First, find the complement of the first language. Okay, so just to make sure that all these are different languages, we do not mix with a state. We just assign the state names, so we will not confuse that this state belong to which machine. So we said this one is x1, x2, x3, y1, y2. We didn't did anything else as it is. Beside assigning the state, we find the complement of that. So when we find the complement of this machine, look at this one. We need to delete this plus sign and add plus sign here. And if you see this new machine, we have plus sign here, and we delete the plus sign from here. So this is the complement of L. Okay, so we just did this. And for to find the complement of this machine, we need to delete this plus sign and add plus sign here. Just reverse the final states. And look at this one. in this machine, we delete the plus signs from here and add the final state. We just give the state name so we do not confuse that this state belong to which language. And this is L2 dash. So we successfully find L1 dash and L2 dash. Look at this one. We find this, we find this. Now we need to perform the OR operation here. L1 dash plus L2 dash. Okay. And you learn this from chapter 7, how we do that. I did not draw those two tedious long table here. I directly did this because my expectation is you understand that you did the assignment for this one. So you know how to do that. And I will find L1 dash plus L2 dash. So once I did that thing, both tables and A and B, from this table, I draw this machine. Okay. Now we did that also. Look at this one. So for De Morgan's law, we find L1 dash, L2 dash, and now we find this thing also. Our final job is take the complement of the resultant machine. So we find this, and now we take the complement of this machine. Means wherever you have final states, delete that. Non-finals will become final. So delete this, this, and put plus here. Look at this one. And this is basically, now this machine is basically L1 intersection L2. What does it mean? We have two machines, these two machines. So the resultant machine will accept only those words which are common words accepted by this machine and accepted by this machine. Union means all words accepted by this machine and or accepted by this machine. Before we did L1 union L2. When we, if you simple perform L1 plus L2, this is union. It means combination of all words accepted by both machines. We are not interested to find the union. We are interested to find the intersection. All common words which are common accepted by this machine and accepted by this machine. Common words. There is a one word. Let's say there is one word. Might be this example is right or wrong, but just giving you one example. Actually, this is right. AA. So AA is a common word. It should be accepted by AA. Now, if there is another word, let's say ABA. So ABA, but ABA. So this will not be accepted by this machine. So this new word will not be accepted by this new machine because it is intersection. It will only accept those words which are valid in both machines. So this is L1 intersection L2, and we can perform this job by applying the De Morgan's law. And this is De Morgan's law. And how you do that? You need to perform the complement and the union operation, and then you will get this thing. Okay, so that's the idea behind that. So now we are saying that when you have two languages and you take the intersection, the resultant thing will also be a regular language. So this will also be a language. So this thing, this machine which you just create, it is also a regular language. So we know that because both are regular and you apply union, and by definition, concatenation will not change. So it will be the regular. So we prove that it is a regular language. The section is also a regular language. And here we finish this chapter. So any question here, guys?
Um, so I guess I'm a little confused on one thing.
Okay.
So here at the end, we're doing the whole table thing where we create the new chart or the new graph um that way. But earlier on in the chapter when we're going over the NFAs, um we were just able to combine the graphs. How do we know when we
That
can
that
do
is
that?
TG. That was not NFA. That was TG.
Oh, okay. So we can only do that with TG then?
Exactly. Only with TG. Okay, so this is now when I give you a question in exam or an assignment, you need to read the question. If question says, please perform plus dot or star operation on TGs, life is easy. You need to perform the way we did here in the early part of this chapter. But if I ask you a question, these are two FAs. I want you to show me the plus or dot or clean star operation, then I am referring to chapter 7 where we perform these two tables and the long process of doing that. FA only work with that way, TGs work with this way.
Okay.
Okay,
Makes sense.
but
Thank you.
but this last part is FA. So how we combine these FAs and find, because in chapter 7 you what you did in chapter 7, you cover uh, L1, oh sorry, L1 plus L2, L1 dot L2. When we say L1, I mean L1 or R1 is same thing. So let's say R1 plus R2, R1, R2, R1 star. But this plus is equal to what? Union. But we did not cover R1 plus R. So R1 plus R2, I can say that R1 union R2. Make sense? But we did not cover R1 intersection R2. So now this is also done by R1 plus R2, but how we find the intersection? So to find that intersection, it is this this De Morgan's law. You can find that this way also.
Okay. Thank you.
Okay. So do you anyone here in this group at this time have anything in mind that without De Morgan's law, are we able to find this R1 plus R2? R1 intersection R2? Do you any idea come to your mind that can we find R1 intersection R2 without De Morgan's law? Any other method? You can think whatever you. Okay, let's say let me give you an example. Let discard. If I open chapter 7 and we go here to this method. Yes, this one, R1 plus R2. This is union, yes, we saw this last time in the slides. So you need to perform some modification here and you can convert this union into intersection. What modifications you do? Anyone? No idea? Okay. Anyone tell me here how we, in case of R1 plus R2, how we choose the final state for Z machine. So we have this Z machine here. How we say that Z4 is the final here or Z1 is final here? How we choose that? You did this, guys. You did this assignment. How we choose the final state here?
If either of those are a final state in their own graphs, then
Amazing, perfect. So now if we change this criteria and we say that instead of either one, if both are mandatory a final state, what does it mean? It means you will get a new machine which will have a final state which will be which will be composed of those scenario where X and Y both are final. And what is this? This is intersection. So you will create a new machine which will accept the intersection instead of union. Here now you are saying, at this time you are saying either X is final or Y is final. That's why it is union. Let's say we put condition here, when both states are final, then Z will be final. If X is final and Y is final, then Z will be final. So then we, by changing this, we convert this into intersection, because now this new machine will, how we say that this is a new machine, because this will be composed of those final states which have been, so in this case what happened, uh, y1 and x3. So if we have y1 x3, oh, it is somewhere down there. So if you do that, so just if you just consider y1 and x3 as a final in the Z machine, then it means that this will be intersection instead of union. Make sense? You guys understand what I'm saying? Guys, do you understand what I just mentioned here? Anyone has any confusion in this? James, do you understand what I just explained?
Yeah, I think so.
Okay. So Riley, do you understand what I just explained, how you convert this previous thing into the intersection? Now I explain you two methods. One is this, or you can follow the De Morgan's law to find the intersection of two FAs. Okay, so you guys are not asking any questions, so silence means yes. I expect that you understand this. Okay, so I think that we done this chapter 9 today, and initially I have planned to go to chapter 10 also, but I think that this is quite good enough for you guys to understand that. So I should stop here. And in the next class, we will start chapter 10. I already published that chapter, so please read that if you have time. We do have a quiz tomorrow from chapter 7, 8, and 9. And we will have exam from chapter 1 to chapter 9 on this coming Saturday, strictly during the class time. Let me stop this recording first.